The unmanned ground vehicle has turned time-consuming and labor-intensive surveying work into something easy and effortless. This is the SafeDoct robot, developed by Save Robtex Company. This autonomous surveying robot can precisely transform construction plans into ground markings with an accuracy of up to 8 millimeters, making building layout work more accurate and efficient than ever before. The operation of this robot is very simple. Users only need to upload blueprints in standard CSV or DXF format into the SafePay software, and SafeDoct can start working right away. After receiving files marked with project coordinates, the robot will autonomously move around the site, spraying paint or projecting lasers at the exact positions where project boundaries need to be marked. The robot is equipped with 2 battery sets, each capable of supporting 5 hours of work. It can connect to any base station and NTRIP network. Specially designed tires allow it to handle various terrains and slopes, whether on mud or sand, and still function properly. With continuous technological advancements and large-scale applications, a new era of construction, one that is more efficient, higher in quality, and safer, is steadily unfolding along the paths laid out by these robots. Seeing this machine shuttling back and forth in such a narrow space, doesn't it look quite unique? Why is it so short? What exactly does it do? Actually, this is a salt scoop tram only 1.8 meters tall. Since this type of salt is mainly found deep underground, hundreds of meters below the surface, it was originally mined manually. But the efficiency was very low, and the cost was very high. That's why this underground scoop tram was developed. To bring it underground, its parts are first disassembled, then transported piece by piece using a lift, and finally reassembled according to the blueprints. Because this scoop tram was specifically designed for such environments, its structure is quite special. The cab is positioned right behind the front wheels, with its height level to both the tires and the body. To solve the driver's visibility problem, cameras are installed in multiple positions on the machine. The operator can then control it from inside the cab using the screen. Its bucket, powered by hydraulic control, can also load and unload in tight spaces. Its efficiency is much higher than manual labor, and if the front bucket is replaced with a gear drum, mining efficiency can be instantly increased. Now, let's take a look at what's called the world's shortest car. It looks like just part of a car's outer shell, no visible cab, no wheels, yet it can actually drive on the road. This was recently built by a car modification team in Italy. They cut off the upper half of a car's body and modified it. To make it roadworthy, the designers installed a small chassis and wheels at the bottom. These wheels are only 3 centimeters above the ground. The engine is directly mounted inside the car. The driver has to crawl in from the rear and drive while lying flat. To see the road, a camera is mounted on the roof, transmitting a live feed to a phone. This car looks bizarre, and driving it is uncomfortable. Not only must you stay in a fixed posture, but you also face dust stirred up by the wheels. Still, it has attracted a lot of attention, with some even asking for it to be mass-produced. Just like tunnel boring machines, after completing large-scale tunnel excavation projects, they are often buried on the spot. As an essential machine for tunnel construction, the tunnel boring machine makes it possible for subway lines to extend across every corner of a city. However, the cost of a TBM is extremely high, with many key components needing to be imported from countries like Germany. Even a small TBM can cost tens of millions of yuan. But here's the strange part. When the tunnel is completed, construction workers often dig a pit at the tunnel's end and bury the machine underground. Why is that? In fact, some TBMs are simply too large and complex to disassemble, making it impossible to bring them back to the surface the same way. Even if disassembly is possible, the costs of transport and hoisting are extremely high. Instead of spending massive amounts of manpower and resources, it's more practical to leave the TBM's outer shell and its heavily worn cutterhead underground, sealed with concrete. Meanwhile, reusable internal components are dismantled in advance and taken away by engineers. Although this method may seem wasteful, in reality, it significantly reduces costs. How are underwater bridge piers actually built? Surely you can't just drain all the water, right? And making the water move aside isn't possible either. But clever engineers have a way. After completing the surveying and determining the location, piling begins. Note that these piles are not directly for building the pier. According to the blueprints, many piles need to be driven into the ground. Then, fences are inserted along the piles into the ground, slowly forming a circle. This circle can also be prefabricated above and then lowered directly into the water. Once the circle is in place, can the water inside just be pumped out to pour the pier? It's not that simple. Since the fence is assembled from pieces, there will definitely be gaps. Even if the water inside is pumped out, water from outside will quickly flow back in. So, engineers came up with another solution. They add another layer of fencing inside. But here's the problem. This inner layer also has gaps, and it will still leak. Adding more layers won't solve the issue. The only option is to pour concrete between the two layers. Once the concrete dries and hardens, it blocks the water. Now you might think it's finally possible to pump the water out. But it's still not that simple. There's another critical step. If the water is pumped out immediately, the pressure inside the circle is lost, and the external water pressure would push the fence inward, collapsing it. To prevent this, engineers install support braces between the fences. With the braces holding up the structure, the fence can withstand the pressure. But another problem arises. Water seeps in from the bottom of the fence. Fortunately, this isn't too much water. At this point, a rebar cage is placed, and concrete is poured to fill the base completely, leaving space for the pier foundation. The next step is lowering large amounts of rebar and constructing the framework according to the design. Then formwork is set up, and the main body of the pier can be poured. After about 10 days, when the concrete reaches the required strength, the fencing can be dismantled. Once all the bridge piers are completed, construction of the bridge superstructure can begin. For deeper waters, the caisson method is used. This involves casting the piers in advance, transporting them to the designated location, and lowering them into place. The caisson is then filled with sand, stone, and concrete inside, enhancing the foundation's load-bearing capacity and stability. Once the pier is fully secured, construction of the bridge continues. It was such a simple invention, yet it directly increased the survival rate of F1 drivers by 17%. It is known as one of the greatest inventions in the history of Formula One. This is the halo system, often nicknamed the flip-flop because of its shape. The so-called halo system is this frame above the driver's head. Doesn't its shape look like a slipper? That's why it was given the friendly nickname flip-flop. It has 3 attachment points fixed to the cockpit of the car, providing head protection for the driver. Although its structure looks very simple, it weighs only 7 kilograms and is made of extremely strong titanium alloy. Tests have shown that in car-to-car collisions, the halo can withstand static loads, up to 15 times the car's own weight. This means the component can endure around 12 tons of impact force, roughly equivalent to the weight of a double-decker bus. You could say it's the strongest part of the entire car. In fact, this life-saving device has only been in use for a relatively short time. F1, with its unique combination of speed and passion, is thrilling to watch. But at the same time, the extreme speeds bring very high risks. In the pursuit of speed, cockpits were fully exposed, leaving drivers' heads outside the car. The only protection for the head was the helmet, which clearly wasn't enough. After countless tragic accidents, the halo system was developed and applied in racing. It protects drivers' heads during crashes, preventing direct impact with the ground. Besides its massive load-bearing capacity, it also blocks flying debris caused by collisions, such as wheels or other car parts, providing drivers with even better protection. Although the halo has repeatedly proven its excellent performance in protecting drivers since its introduction, its shape has been criticized from the start. One major reason is that it obstructs vision. From a driver's perspective, a pillar appears right in the middle of their line of sight. Another concern is that in F1 racing, where every gram matters, the halo adds weight and slightly affects aerodynamics. Many teams had to redesign their cars to adapt to the new component. Despite these drawbacks, since its introduction, the halo has indeed shown powerful protective effects. That's why it is still in use today, and is regarded as one of the most important safety features in racing.